In the 21st century, battery-powered embedded devices have become a part of everyday life for many people. Unfortunately, so has the need to frequently recharge or exchange batteries. While it is unlikely that this will go away anytime soon, developers can still maximize the time between charge cycles by optimizing their device's energy consumption. Energy models are a helpful utility for this. They allow developers to simulate the energy consumption under different configurations and workloads without the need for long and repetitive measurements. However, before an energy model can be used, it needs to be generated, preferably without requiring expert knowledge about the device in question. The regression model trees I'm presenting in this video address just that by automatically generating energy models that are both accurate and understandable, thus allowing reasoning about what exactly is causing power consumption and which configuration options are most promising for optimizing it. For the purpose of this video, an energy model is a function that maps the device configuration, for instance, data rate and transmit power of a radio chip, to an energy attribute such as time and power consumption of its different operating modes, or in case of a BME680 environmental sensor configuration to average power consumption. When it comes to automatic generation of such an energy model, we are essentially talking about machine learning. So given some device configurations and corresponding measurements, for instance, power measurements of the BME680 sensor, we can use a suitable machine learning algorithm to obtain an energy model. For simulation purposes, this is fine, but such an energy model is not really meant to be understandable by humans. In the general case, it's just a magic black box where device configuration goes in, predicted power consumption comes out. For instance, here is a classification and regression tree, which is pretty much a standard machine learning model for this type of task that has been automatically generated based on the BME680 measurements. If we zoom in, we see that it's basically just a decision tree. With a model error of less than 7%, it's also sufficiently accurate, but with a model size of about 1000 nodes, it's not exactly easy to understand why the device is behaving the way it is behaving just from looking at the tree. In contrast, here is a regression model tree that has also been automatically generated from the same observations. Here we immediately see what's going on and why. So we see that both the device's power mode and whether or not air quality measurements are enabled affect how the device behaves. In sleep mode, it uses a static power consumption of about 85 microwatts. In active mode with air quality measurements disabled, the oversampling configuration also affects the power consumption. And in active mode with air quality measurements enabled, both the time and temperature of the heated metal oxide plate, which is used by the sensor to detect the presence of pollutants in the air, also affects its power consumption. This regression model tree also has a model error of less than 7%, but, well, is smaller by 2 orders of magnitude and therefore much easier to understand for humans. Next, I'll explain the idea behind regression model trees and the key concepts used for automatically generating them, and then show how regression model trees compare to other machine learning approaches, both in terms of accuracy and model complexity. The basic idea behind regression model trees is relatively simple. First, we use classification and regression trees to generate a decision tree that describes how Boolean and non-numeric configuration variables affect the device's operation. Then we use an extended version of prior work of us to automatically generate model functions that describe how scalar configuration variables affect the device in the individual leaf nodes of the tree. Both tree structure and functions are generated automatically. To illustrate generation of regression model trees, I'm going to use the BME680 measurements again. Here we have 2 Boolean configuration variables and 3 scalar configuration variables. Regression model trees are generated in a top-down manner, so we start with the tree structure. This algorithm is quite similar to the algorithm used for classification and regression trees, and basically looks at different variables analyzes how they affect model quality, and chooses the one which is most beneficial for model quality. So here, first we look at the air quality variable, generate a model where air quality measurements are disabled, generate a model where air quality measurements are enabled, and calculate the loss of this model, which in case of regression trees is just the sum of squared residuals. We do the same for the operating mode variable, and then compare the loss of the various variants. In this case, we find that the air quality variable leads to a slightly more accurate model. So the generation algorithm selects this variable and transforms it into a new regression tree node. It then continues recursively and generates subtrees, and this is the resulting tree structure, which only lacks functions for the leaf nodes. So let's look at those next. Now, before we can find and fit a function, we first need to determine which variables are relevant and should be included in the function, and which variables do not affect device behavior in this case and should therefore not be included in the function, both to decrease model complexity and to minimize the risk of overfitting. By the way, we do this not just here, but also during tree generation. So variables which have no effect on the device's behavior do not become part of the regression tree structure. The idea is, again, to look at different splits of observations and determine how ignoring a single variable affects model quality and by how much. To illustrate this, let's look at measurements for active mode with air quality measurements disabled. First, we generate a lookup table model where all configuration variables are fixed. Nothing is variable. So this model basically captures the underlying measurement error. Here we see that it is quite accurate with a model error of roughly 10 microwatts. Next, we start ignoring or varying individual configuration variables. First, let's look at the heat time. In this case, we find that ignoring the heat time does not have a significant impact on model quality. The error is still roughly 10 microwatts, so heat time is not relevant in this case. Same goes for heater temperature, still 10 microwatts, also not relevant. However, when ignoring the oversampling variable, both we and the algorithm see that it does have an effect on the model. Now the model error is an order of magnitude higher, and therefore the oversampling variable is relevant. Now the algorithm needs to find out how exactly oversampling affects device power. To do this, it uses ordinary least squares regression and a set of domain-specific function templates that are built into the algorithm. For instance, linear, inverse, exponential, and logarithmic functions. It fits each function candidate on each set of measurements, calculates the model error of the fitted function, and then decides or calculates which function has the lowest error. In this case, it finds that a linear function wins in all cases. So by majority vote, the effect of oversampling configuration on device power consumption is linear. This function template is fitted on all measurements again and becomes the model for this specific tree leaf. Now let's see how regression model trees compare to other machine learning approaches. For this evaluation, we use the BME 680 measurements again, plus receive and transmit measurements of two different embedded radio chips. Our model lineup or comparison consists of classification and regression trees, so basically piecewise constant functions expressed as a decision tree, linear model trees, which extend classification and regression trees with a bottom-up pruning step that transforms individual subtrees into linear functions, extreme gradient boosting, which is an ensemble or forest of several classification and regression trees, and finally our contribution, regression model trees. First, when it comes to model complexity, we clearly see that regression model trees are least complex in all cases. In fact, in 4 of 7 cases, our regression model tree algorithm generates a model that consists of just a single node, So there is no tree structure, just a single function that has been automatically generated and fitted on the observations. In all other cases, regression model trees are still the smallest model. Linear model trees also perform quite well, whereas classification and regression trees and gradient boosting are quite large, typically with hundreds or even thousands of nodes in the tree. So nothing that can be understood easily just by looking at it. Model accuracy, however, interestingly shows almost no relation to model size. Here we see that regression model trees are pretty much as accurate as the other approaches. There's just one exception when it comes to NRF24 transmit power. We see that linear model trees and regression model trees are slightly less accurate than classification and regression trees, but still achieve a model error of less than 7%. In conclusion, I have presented regression model trees, which are generated entirely automatically, are accurate with a model error of less than 7% after cross-validation, and still small enough to be interpretable by humans. Of course, they are not a one-size-fits-all solution, but specifically tailored towards embedded devices with a relatively low dimensional configuration space. Also, currently, regression model tree generation works best when performing an exhaustive state space exploration. However, there is literature concerning data-efficient generation of classification and regression trees, and we are confident that it can also be applied to regression model trees. Nevertheless, I think regression model trees are a useful addition to the toolset of the embedded developer. Details about our algorithm as well as source code are referenced in the paper.